Welcome, everybody. My name is Ulrike Young, and I'm very excited to present to you the first webinar of this year in the Supercomputing Spotlight series of the SCIAM Activity Group of Supercomputing. Our speaker today is Dr. Lori Diachin, and Lori has been the director of the US Department of Energy's Exascale Computing Project, or ECP, which has successfully delivered capable exascale computing ecosystem. So Lori is also the Principal Deputy Associate Director and the Computing Directorate of Lawrence Livermore National Lab, which has about 1,400 staff members. She has over 30 years of experience in high-performance computing and applied math research, and co-authored more than 50 publications. Before joining Lawrence Livermore in 2003, she also was employed at Argonne National Lab and Sandia National Lab. She received her PhD in applied math from the University of Virginia in 1992. And there's a lot more to be said about her, but I don't want to use up all the time because she has a lot more interesting things to say about exascale computing, about this whole project. So I'll just give it over to you now, Lori.
All right, well, thank you, Ulrike. And I just want to say how happy I am to be able to give this presentation to the SCIAM HPC supercomputing community. It's been an absolute joy to work on this project, and I'm excited to share with you some of what we learned and what we accomplished along the way. So the Exascale Computing Project, which I will refer to as ECP pretty regularly, was designed to help launch the exascale era. So it was started in 2016, and it was funded by the United States Department of Energy, both their Office of Science program and their National Nuclear Security Administration programs. So it was designed to be a 7-year project, funded at about $1.8 billion. So it did have a fair amount of resources that were able to be used to really bring the community in the Department of Energy and more broadly into the exascale era. So this funded over 81 different research teams from across the Department of Energy. There are 17 labs in the Department of Energy system. We funded 15 of those. We funded almost 60 university partners and almost 40 industry organizations as well. So because of the duration of this project and the scale of this project, it really was a unique opportunity to bring together various different discipline experts in applications from a wide variety of areas and software, computational science expertise. And really our goal was to move application codes and the software ecosystem from where it was at the beginning of the project to be ready for the exascale computing era. So we trained well over 1,000 researchers. When we look back at our payroll, there were over 3,000 people who were funded by the ECP at one time or another, and really brought along the next generation through funding over 1,000 students who have been introduced to high performance computing, GPUs, and what's needed for exascale. So the technical work did complete, mostly complete by December 31st of 2023 and was fully completed by March 31st, 2024. And we're really now working on, finalizing the project and closing it down. So when we started in 2016, we were tasked to meet 4 mission needs for the Department of Energy. So because it's a formal project, there were mission needs statements that were written. The 2 that I'm going to focus on most in this presentation is really around the delivery of the long-term sustainable software ecosystem that can be used, we believe, for years to come. And then looking at the mission critical applications and ensuring that those exascale systems that have recently been deployed at the Department of Energy labs were ready to use basically day one. In addition, we had work that was designed to help promote the health of the US high-performance computing industry by investing in our industrial vendor partners to do research that would be impactful to the exascale systems. And then also, maintaining leadership in high performance computing. But like I said, I'm mostly going to focus on these first two mission need areas for this presentation. So to meet those mission needs and to basically structure the project so that it could be successful over the 7 years and the 1,000 researchers and the 81 teams, we really had to set it up in such a way that there were manageable pieces. And so there were 3 large pillars of technical work that we developed. One was in application development, led by Andrew Siegel at Argonne and Eric Draeger at Lawrence Livermore, where we funded 24 different applications from a wide variety of areas in 6 co-design centers. The second area was software technologies. This was led by Mike Haru at Sandia National Labs and Lois McGinnis at Argonne National Lab. And this is where we really focused in on the libraries and tools that are needed to help ensure applications are successful. And then finally, there's the hardware and integration component. And this is where we funded research with the vendors. It was led by, at the end of the project, Richard Gerber at Lawrence Berkeley National Lab and Susan Coughlin at Argonne National Lab. But it also really helped with facilitating the deployment of the applications and the software technologies on the DOE systems as they were being delivered. So this community, I'm sure, is very well aware of the fact that there are now several exascale capabilities that are cited at the DOE laboratories. So in particular, the first system that came online was the system at Oak Ridge National Laboratory. That's the Frontier system, which was a combination of AMD CPUs and GPUs and was, put forward by HPE. Just at the most recent ISC conference, it's still number 1 on the top 500 list and has been since May of 2022. And their HPL number was almost 1.2 exaflops. We're also looking at these exascale systems for how they do with respect to mixed precision performance so that they're used and considered for a combination of more traditional simulation codes and also artificial intelligence, machine learning type codes. So Frontier is the number 2 system in that mixed precision HPL number with 10.2 exaflops. ECP got access to this machine basically in October of 2022 in a very limited fashion and had full system access starting in April of 2023. And it's just been an excellent system. So many Gordon Bell Prize finalists and winners have done work on the Frontier system, and it's just achieved a whole host of first-of-a-kind science goals. The second system that's been deployed is the Aurora system. This is an Intel system, and it's located at Argonne National Lab. The full system was completed in June of 2023, and they now are number 2 on the top 500 list, just breaking the exaflop barrier, but only using about 87% of the machine. And so as they continue to bring more of the machine online and use it at scale, we do expect this number to go up. It was number 1 on the mixed precision HPL number at 10.6 exaflops. So we also expect this to be a great resource for a mix of traditional and machine learning type applications. And the ECP got access to this system in July of 2023 and full system access just last November. And then finally, the third exascale system that's being deployed by the Department of Energy is being delivered to Lawrence Livermore National Lab, where I'm located. All the cabinets have been developed, deployed and tested. The networking's been deployed and tested. We're receiving the boards now, and we expect to have this system up and running later this year, and we expect it to exceed 2 exaflops when it is running. This machine is largely going to be used for stockpiled stewardship, so it will be flipped over to classified use after a very brief period of open science later this year or early next year. So in order to make use of those systems, the ECP really invested in a broad range of critical application areas. that were important to the Department of Energy. And these ranged from, climate simulations to energy type applications, material science applications, national security, of course, for the NNSA, really designed at looking at basic science, national security type applications, economic security, and competitiveness. Some of these applications, when the project was launched in 2016, were already performing really well on the petascale systems that were available in 2016. So these were 12 to 15 petaflop systems back then. And some of these applications, however, were not necessarily already being used in high-performance computing environments. So in particular, applications like the power grid were really new to high-performance computing. The additive manufacturing application that we have had components that had been used in high-performance computing, but used as a group were not necessarily high-performance computing ready in 2016. And so we had two different ways in which we measured our success in making sure these applications could perform on the exascale systems. And in general, they wildly exceeded our expectations. So 11 of the projects that I just mentioned were already ready to go on petascale systems. And so we ran a baseline calculation in 2016 on the high performance computing systems that were available then. And those applications were required to not only demonstrate exascale capabilities and brand new science that could only be done with exascale computing, but also achieve a 50x performance improvement in their science work rate. So how many floating point operations they're doing on a particular discretization scheme, or just whatever they defined that made sense for their science. And so you can see that 10 out of 11 of those projects surpassed that goal of both achieving the exascale capability and doing it 50 times faster, at least 50 times faster than they could in 2016. And I want to point out that this is a logarithmic scale. And so you can see that many of our applications actually achieved several hundred times faster. And I'll talk a little bit more about EQSIM, which was almost 3,500 times faster than where they started. And that's a mix of algorithmic improvements and also, the new capabilities for the machine. For the other applications, so 10 of the Office of Science projects and the 4 NNSA projects that were developing brand new capabilities for high-performance computing, their target was to demonstrate those capabilities on the exascale system and make really good use of the architecture and the system at scale. So they had to use at least 50% of the nodes, and in this case, take advantage of the GPUs. And so we had 9 out of 10 of our science projects reach that goal, and 3 out of 4 of the NNSA applications reached that goal. So just very, very successful in terms of demonstrating what can be accomplished with exascale computing. So this is the example I'll talk about in a little bit of detail. I don't have time to talk about more than really one example. So when the project started, for the earthquake simulation code, it was a CPU only code. It was written in C, largely by physicists and applied mathematicians, which is great. And it had a lot of complex nested loops, which we know don't necessarily work all that well on GPUs. And so many of the accomplishments that this team achieved ranged from algorithmic improvements where instead of using the meshes that they had at the time, they used curvilinear meshes with refinement in order to improve the scientific work rate. They rewrote their code into C++ so that they could take advantage of abstractions, which I'll talk about later, that allow them to have good performance portability across different GPUs. They took advantage of data compression libraries. And there's now a strong coupling between an earthquake simulation code and a structural mechanics code that looks at modeling buildings for a particular earthquake. And so I'll show a movie here. So this is an earthquake simulation on the Hayward Fault. It's a magnitude 7 earthquake. You see the yellow star is where the earthquake started, and the red dot is where this 12-story building lives. And they're able now to do these earthquake simulations at a resolution that is fine enough that they can actually model the soil motion at a resolution that is useful in the context of looking at particular buildings. So it's the first time that we've ever really been able to look at that combination of the earthquake simulation, the soil and how that's impacting the soil, and then how that's then impacting the building. And not only can you do that for one location, one scenario, one building, we now have the ability with exascale computing to do this for many different realizations. And so here's, an example where the earthquake started at a southern point on the Hayward Fault, and then at a northern point on the Hayward Fault. And then over here, you're seeing basically the sort of the distortion maps that we would expect for the soil and for buildings in these various different locations. And so now we can run many different scenarios, different realizations of an earthquake on the Hayward Fault, take a look at the resulting damage maps, and get a sense really of what that earthquake hazard assessment is for this fault. And so again, a completely new capability that is game-changing in how we think about earthquake assessment, earthquake risk assessment. So very excited about that. Ulrika and I were talking earlier, I live about here, she lives about here. And so we don't really like to look at these maps very hard because they are a little bit scary. So there are lots of key ingredients that go into making a successful application project. And I'm going to talk a little bit about these in some detail, but it ranges from the algorithmic innovation. So for example, in the earthquake simulation I just mentioned, the curvilinear mesh refinement, making good use of the GPUs, and then integrating a lot of advanced technologies and math libraries and other computer science tools. So one of the things that we found that was really critical for the Exascale computing project was just how much the hardware can drive the algorithmic choices that you are making. So the GPU systems, do vectorized type operations really, really well. They don't do branching algorithms very well. And so there's a lot of work that was done to really take advantage of those GPU systems. So increasing the number of dimensionality and the parallelism that you can feed into the GPUs. So for example, in various different atomistic and molecular dynamics simulations, taking advantage of fragmentation methods where you can break up the domain in ways that maybe didn't make a lot of sense on CPUs, but now make a lot of sense on GPUs. Doing high order discretizations to maximize the fact that you can get a lot more flops for every bit of communication that you're doing. And then, looking at reducing branching. So for example, in various Monte Carlo simulations, instead of looking at, particles on a particle by particle basis, and following each particle through its lifetime, you would instead want to group those particles into particles that are experiencing similar kinds of events, and then be able to do a very fast loop through those particles without having to do a lot of branching. So those are the kinds of algorithmic adaptations that the applications teams made in order to better leverage the kinds of architectures that were going to be available on the GPUs. And so, one of the points that I want to make, and I'm now going to switch over to porting, is that the high performance computing systems, when ECP started, were a mix of CPU only machines, and then there was one system that combined CPUs and GPUs, and those GPUs were NVIDIA GPUs. And NVIDIA pretty much dominated the landscape, even through our pre-Exascale systems, Summit and Sierra at Oak Ridge and Lawrence Livermore. So, there was a lot of NVIDIA. It's very mature. The software stack is very mature for NVIDIA, and there was a lot of experience using those kinds of GPUs. But as we moved into the Exascale era, we found that, we have more GPUs that we need to be able to leverage. So NVIDIA is still in the mix in terms of, our capacity machine Perlmutter at Lawrence Berkeley National Lab. But at the Exascale systems are a mix of AMD and Intel GPUs. And so teams really had to be designing with performance portability in mind from the very beginning. And so this is just a high-level graphic that basically showed the steps that a lot of the applications went through as part of the ECP in their porting process, going from many core CPUs, where they didn't use GPUs at all, to looking at CPUs plus GPUs, perhaps using native programming models, to now looking at multi-GPUs, so 4 and 6 GPUs on a particular board, to really making everything GPU resident, so maximizing the performance by minimizing the data motion between the CPUs and the GPUs by just bringing everything into the GPUs, and then doing that across many different kinds of GPUs. And so these were sort of the logical steps that the application teams needed to take. And to do that, there are lots of different programming models that you can choose to use to achieve this performance portability. And our teams experimented with all of these. So for example, you can use GPU-specific kernels. So these are the CUDA kernels that NVIDIA provides, or HIP or SYCL kernels for AMD and Intel. And you refactor the code to work well with that GPU, but it is specific to those particular kernels. You could also, if you're using C++, move to more abstraction-based layers where a lot of that specific kernel code is abstracted away. And there are lots of tools that have been developed to do this. There's a lot of work in this. The two that have been most used by the ECP teams are the Cocos abstraction layers, developed largely at Sandia, started at Sandia, but now developed in many different places, and Raja, which is a very similar technology developed at Lawrence Livermore and used a lot by the NNSA applications. Some folks have experimented with the loop pragma models using, OpenMP offload, OpenMP or OpenACC. Largely, this was used in our Fortran codes. And then finally, at the highest level, you could use co-design frameworks where they're designed with specific motifs in mind, so adaptive mesh refinement, high-order discretizations, et cetera. And those frameworks abstract away the specifics of the particular architectures that you're working on, and so you can get co-design or performance portability through those co-design centers. And what we saw over time was that the languages that the exascale computing applications used really migrated. So when we started, so we have about 60 to 70 codes that are part of our application portfolio. When we started, about 20 of those used Fortran, and by 2022, that had reduced to about 10. And C and C++ had similarly, increased. So a lot of folks took this opportunity to migrate from Fortran to C and C++, and it's for a variety of reasons. We see that a lot of vendors are supporting C and C++ more completely, more readily than Fortran, and so it's just a risk mitigation strategy that a lot of code teams took this opportunity to take advantage of. And then for the programming models that I just mentioned, the native GPUs, loop pragmas, the C++ abstractions, and the co-design libraries, you can see that there wasn't one clear winner, I would say, for what the application teams chose to do. I would say a lot of them started out using the native GPU and loop pragma type models because those were widely available and well understood at the time. But by the end, a lot of them were making the move more toward the C++ abstractions and co-design libraries. And what that allowed the teams to do is very quickly port to different GPU architectures. So if you recall, I mentioned that we didn't really get access to the Aurora system until 2023. And yet you can see that there were a number of code teams, and these are the early science teams and ECP teams who were able to do sort of performance comparisons between the Ponte Vecchio GPU, which is what's on Aurora, and the MI250X, which is the GPU that is on the Frontier machine. So, one is parity, Greater than 1, the Ponte Vecchio is doing better. Less than 1, the AMD GPUs are doing a little bit better. And similarly, folks were able to do the same sorts of experiments, comparing the Ponte Vecchio GPU with the NVIDIA A100 GPU. So I think what's really nice here is that you can see you can get really good performance with a lot of these performance portability abstractions and layers, and that you're able to take advantage of different kinds of architectures, GPU architectures in particular here, quickly. And so we hope that this is in some way, future-proofing these application codes for the increased specificity that we expect to see in architectures specialization that we expect to see in architectures going forward. So now I'm going to switch my attention to looking at software infrastructure. So the applications relied on a lot of different tools for their success, ranging from the programming abstractions I just talked about for GPUs and CPUs, to solvers, preconditioners, a lot of math libraries, to data management and visualization tools, discretization infrastructure, and then really building and deploying these applications and all of their dependencies has become quite challenging on the systems that we see today. And so there were a lot of people who took advantage of tools like SPAC to help manage that process. So the ECP invested in 6 different software technology areas, ranging from programming models and runtimes through development tools, such as compilers. So we invested in open source compiler development for OpenMP, for Fortran, math libraries. So a lot of work in both sparse iterative and direct solvers. Mostly sparse systems are what we saw, looking at performance on the new architectures. In data and visualization, really focusing in on the cost of data movement and doing things in situ to reduce that, along with compressing information so that you have less data to move. And then finally, the software ecosystem. So for example, the build features, the software deployment mechanisms that we're using. I'll talk a little bit about E4S in a moment. And then just optimization of this for things like the cloud and use of containers. So we deployed our technologies primarily through the extreme scale scientific software stack, which I'll refer to as E4S. So when ECP started, a lot of ST products were developed by teams and just deployed directly by those teams into applications. And where we wanted to take the software stack is basically up this column through software development kits, that combined like things together. So for example, the XSDK kit is largely focused around our math libraries. And then those SDKs are then deployed through E4S. So by the end of ECP, we had deployed, E4S with well over 100 release products that were tested. And one of the nice things about this software portfolio is that it's open source, it's ready to go, folks can take advantage of it, and it had a lot of community backing behind it in terms of developing policies for software quality and what that would mean, looking at, a turnkey, user experience where they can build different things together, looking at build caches to improve build time. So lots of different aspects to this. And I would encourage you, if you haven't already, to take a look at the E4S website to get more information about E4S. I think one of the things that I really found interesting about E4S was the multi-layered testing that's done to make it really much more turnkey. So there's the testing of the individual libraries, and this is showing the interoperability matrix for the math libraries software development toolkit. So test those individually, then testing the interfaces between particular libraries, that making sure those are working, testing subsets of those interoperable packages in combination with each other, and then finally testing the whole SDK so that if anybody wants to use any subset of these math libraries together, they can know, because all of this testing has been done, that they will work well out of the box. And a real prime example of that is really the AMRX adaptive mesh refinement package developed at Lawrence Berkeley National Laboratory. So they had a large number of applications that were depending on them for adaptive mesh refinement. And at the same time, they had integrated pretty heavily with a lot of different math libraries, the PETSI library, sundials, nonlinear solvers, the hyper algebraic multigrid libraries, tools for visualization and I/O, the build tools, and applications by working through AMRX got access to all of these capabilities, and we knew that it was well tested and ready to go. So I just think it's just a really nice example of that integration working for a wide variety of applications. So there's lots of different integration examples. We really encouraged our teams to work together on these things. I'm only going to, again, because of time, focus on one. I'd like to take just a quick look at the power grid application. So if you recall, this was one that I mentioned at the beginning of the talk that wasn't necessarily ready for high performance computing at the beginning of the project. And one of the real barriers that this team ended up facing was in the solution of the linear systems that they had. So their sparsity patterns were typically pretty, maybe not quite random, but pretty random. And so they weren't able to leverage, a lot of the techniques that had been developed for, supernodal type systems to take advantage of BLAS and LAPACK. And so we really needed to develop new solver strategies for GPUs for these kinds of systems. And so there turned out to be a really strong collaboration between the power grid application team and the Super LU and Ginkgo teams to develop these, non-supernodal structures and solvers that could be really used well on GPUs. And so this team, they actually worked for several years to develop these solvers, basically Cholesky type solvers for symmetric and LU for non-symmetric type systems. And you can see the performance for these systems, on the GPUs, they're doing really quite well. So, this is on the AMD GPU. And as the GPUs are getting better, the solver performance is getting better. So we expect to see really good ongoing performance from these new solver capabilities that were developed as part of the ECP for these kinds of systems, that show up not only in the grid, but in other engineering applications as well. So I just thought this was a really nice example of a collaboration between, the math libraries, this community, and one of the application teams to highlight. So we're capturing our lessons learned in these various different areas and sharing them in venues like this, performance portability, the models that folks used, the strategies that particular applications used, how folks went from GPU accelerated to GPU resident in their application codes, the value of collaboration. I think one of the things that was so great about this particular project was just the fact that for 7 years, application teams could work closely with mathematicians and with computer scientists. And the amount of innovation and the success that you can have when you have that sort of long-term collaboration was really remarkable. As I showed in that slide at the beginning of the talk, where teams achieved not just 50x performance improvement, but hundreds of times performance improvement in their work science rate. And then in the software ecosystem, I think one of the big legacies for the ECP is this idea of software as a facility. When we build facilities, we build in maintenance and operations phases, and we need to be thinking about our software in the same way. And so the fact that E4S put together this coherent software stack for high performance computing that is used not just by the DOE, but is also used by HPC centers, for NSF and, internationally, and it's now being used on the cloud in various container type deployments. That idea of software as a facility is really powerful, and it has a lot of promise. So what's next for our ECP software? The one thing I'll highlight here is the PESO project. So the leadership team for ECP in the software technologies area developed a proposal to Oscar for this Partnering for Scientific Software Ecosystem Stewardship Opportunities. So it's a project for software stewardship that's focused in on partnerships, stakeholder engagement, community development, such as the Better Scientific Software Fellowship Program, the services, largely focusing in on SPAC, continuous integration, and E4S for the products. So encourage you again to take a look at this website. And this is part of the broader software stewardship effort that was recently funded by the DOE's Office of Science, where there are 7 projects that are funded through this effort. PESO is one of those, and they've developed a consortium where many of these projects have distinct and complementary goals. So PESO is really involved in the larger ecosystem pieces like SPAC and E4S. Rapids and Fast Math are focused in on the integration and stewardship of the individual tools, for example, some of the tools that I mentioned earlier. And you can see there's, focuses on scientific workflow systems, performance and behavior, et cetera. So there is a web page for this consortium, and I encourage you to take a look at that as well. So just want to conclude by saying we delivered on our mission needs. We deployed E4S at the high-performance computing facilities, again, in the United States, around the world. There were 76 products that we developed as part of ECP that are available for computing at all scales. One of the things that's really nice about the work we've done was a lot of it was really focused on that on-node performance with how do you really take good advantage of GPUs. So that can be in an exascale system, it can be in a department scale system, it can be on a single system, on your laptop if you've got GPUs. So you can take advantage of this work at all different scales. And then ensuring that we could deliver on those mission critical applications. And I showed you just 1 or 2 examples, but we have so many great stories about results that we were able to achieve through these collaborations, through the work that was done on ECP that really advanced simulation science in those areas. And a lot of that is paving the way for new applications in industry, in academia, et cetera, to be able to leverage this accelerator-based computing. And so, I may be biased, but I think that our impact and legacy will be really long-lived. So we've talked about the applications, we've talked about the software stack, we've talked about the researchers that have been trained that are now ready for looking at specialized hardware, particularly accelerator-based. We have some best practices for running a project at this scale. And so really, taking a lot of this and trying to get the word out to the broader community to move the whole nation and the broader community forward in the use of these kinds of systems. So with that, I'll just highlight, of course, this has been the effort of thousands of people. I was able to highlight a few key examples here, but I want to thank the entire ECP, particularly our leadership team who contributed to what I was able to talk about with you today. And with that, I will conclude and see if there are any questions.
Thank you, Laurie. This was really a very good talk. I really enjoyed it very much. So if you have any questions, you can either put them in the chat or there's a question and answer. So far, I don't see any questions, so please feel free to do so. But as we're waiting for some questions, I have a question for you. I know you didn't get that much time, but if you had a little more time, which other thing would you have mentioned?
Oh, gosh. There are so many things I could mention. I probably would have spent a little bit more time on some of the algorithmic innovations that were done in terms of lessons that we've learned about things that work well on GPUs. I think this audience would have been very interested in that. I only got to do a very high level, broad brush at that. I think I would mention some of the workforce development programs that we funded as part of ECP to broaden participation. So we funded a lot of training programs, like the Argonne training program was funded through ECP for the last 7 years. We had a broadening participation initiative where we funded interns at the national labs to work on ECP projects that reached well over I think it was 300 students in the end. And then we had an intro to HPC boot camp that we developed that I thought was really great, that we only were able to do one session of at NERSC last summer, but we brought in 60 students from underrepresented communities just to introduce them to high performance computing and talk to them about energy justice and how high performance computing could be used in a topic they really cared about. So that was really well received, and a number of those students have now applied for internships at the labs. So those are some of the things I would have mentioned. I might also have mentioned some of our work with our industry and agency council that was bringing along our various industry members, agency. There's some really nice examples from GE and NASA about what they've been able to do on exascale computers. So those are things I would have talked about.
Okay, well, thank you.
I could have given a 2-hour talk.
I know. We only gave you like 30 minutes, and so you did a little longer, which was great. I really, really enjoyed it. So we don't have any more questions. So I think you did such a great job that people felt all their questions. Oh, wait, there's some popping up. Okay. So here's one question from Emily Schemann. I hope she says, for code developers who were not involved in ECP and are still running on CPU only, how do you recommend people to start to port codes to GPUs? Any specific common tools to leverage or high-level guidance?
Yeah, so it really depends a lot on the algorithms that you're using, the programming languages that you're using. We found a lot of good success in rethinking, algorithms, as I mentioned at the beginning, to reduce branching statements. There are various optimizations that can be done. There are the abstraction tools that are now relatively mature. The COCOS model's been under development for many years and is now pretty mature. And so, taking advantage of those kinds of technologies to ease your way, I think is really useful. So those are some of the things that I might recommend, but one of the things that we found is that it can be application specific. So without knowing more about specific applications, the specific application, it's hard to give specific guidance and advice.
So there's another question from Sabri Blana. Are there plans for Exascale computing?
There's a lot of discussion about what is next for computing. I know that folks at Argonne, Rick Stevens in particular, is talking a bit about Exascale computing. Exascale was, it's a nice, I don't know, word, I think, but really we're all on this journey for high performance computing that's not going to stop at exascale. So I think there's a lot of discussion now around what's next for computing. There's a lot of discussion about how we can better leverage things like artificial intelligence, machine learning to get that next boost for our applications. And yes, what does a Exascale machine look like? What are the various different specializations in the hardware that we want to be able to take advantage of to continue to get these boosts in performance that we saw going from petascale to exascale?
Seems like now we get a whole lot of questions. Let's see how many we can still answer. Like here's one. How are these legacy Fortran codes going? How much effort will put to make them run on GPUs? Possibly with the help of high-level layers like COCOS and Raja.
Yeah, so the Fortran codes unfortunately cannot take advantage of COCOS and Raja. Those are both specifically for C++. And so C and C++ codes can take advantage of them. Some I am aware of some, largely Fortran codes that rewrote their kernels in C and C++ so that they could take advantage of COCOS and Raja. But the Fortran codes, largely took advantage of OpenMP and OpenACC. And in some cases that worked really well and it was pretty seamless. We did have one code that encountered a pretty nasty bug in OpenMP, and they're still working through getting that resolved. And so I would say in general, they're going well. I think one of the concerns that the community has is the ongoing support, as I mentioned earlier, for Fortran compilers. and what that looks like in the long run from the vendors. And so I know the Department of Energy is making investments in continuing to support Flang, which is an open source Fortran compiler. I know a lot of the vendors are starting to turn their attention to also supporting Flang and using Flang as their Fortran support. And so that was one of the reasons many codes chose to take this opportunity to start migrating to C and C++.
So there was another question along this line. Would you recommend abandoning Fortran? Is CUDA Fortran worth it? I guess we need more than CUDA Fortran, I'm assuming, but anyway.
Yeah, so I mean it's going to be very, very dependent on the use of your code, how deeply ingrained it is in your applications. I know there are many Fortran codes at the Department of Energy, at NOAA, for example, the National Ocean and Atmospheric Agency, I think it's the last day. But anyway, there's a lot of Fortran code that still exists that is well understood. It's been verified and validated to the nth degree, and it would be very hard to move away. So it's very hard to just completely say, yes, I recommend you abandon your Fortran. I can't say that in good faith, given how much effort has gone into some of those codes. I'm just saying that there's concern about the support for Fortran going forward. And so it's just something to keep your eye on.
So there are various people asking about what you're thinking about quantum computing. Like, what are your thoughts on its useful and timeframes for quantum computing?
So I'm not an expert on quantum computing. I would say my very limited personal opinion is that I think we see a lot of promise in many of the experiments that are being done with quantum machines of different types right now. At Livermore, for example, we're working on superconducting quantum computers, but I still think they're a ways out in terms of their ability to be practically useful in a cost-effective manner. So, but I am not the expert. So I would encourage you to talk to folks who are much more deeply embedded in that community for a more realistic assessment.
Then here's a question. Do you have any insights to share on the state of developing better proxy applications to improve scaling codes onto exascale systems?
Let's see. So we had an effort as part of ECP that was looking at developing proxy applications that did some really good work in terms of preparing, you know, the vendors for the kinds of applications that we would need. So I would say there's still a lot of work in the development of proxy applications, particularly at the national labs that are deploying these large-scale systems. So they all have, you know, benchmark applications and proxy applications that are used to ensure that the machines are meeting the performance goals that are in the contracts for the delivery and deployment of those machines before they are accepted. And so I think there's still a lot of really good work going on in proxy applications for the procurement of these systems. I'm not sure if that answered the question, but
yeah, okay. That's just, oh, yes, we have, well, there's one question. I don't know if you have an opinion on if instead of using C++, Rust as a memory safe language should be used. I know people are talking a lot about Rust nowadays.
Yeah, I don't have a strong opinion on that. I guess one question I would have is, you know, the ecosystem around Rust and you know how fully developed that is. So I actually don't know the answer to that question. I don't have a strong opinion.
Yeah, I think, well, okay.
So I see, you know, so I brought up the Q&A, I found the button. So there's a question, you know, can we use CUDA on Intel GPUs? There are a lot of work that's been done to develop basically performance portability tools that allow people to easily translate CUDA code into, for example, sickle code that can be used on the Intel GPUs, or a lot of people when they first started moving to AMD used Hipify, right, which was a translator for CUDA into HIP. So those kinds of translator tools are being developed and are seeing some success. And so I know that the folks at Argonne are continuing to invest in those kinds of tools to help make it easier to get onto the Aurora system. If you already have a GPU code that's either HIP or CUDA, making it easy to get onto the Intel GPUs. So they are continuing to make investments in that area.
So I guess let me give you one question I was higher up, a more like kind of critical journalist type question. The question was, what do we need Exascale for? Isn't it too expensive? I know you did talk about someone we needed Exascale for, but
yeah, so I guess it depends on what you're saying is too expensive. If you're talking about the hardware investments, if those were too expensive, or if you're talking about the software stack, which I would argue is not just for Exascale, it's actually for the entire stack. I believe the future is in these accelerator-based architectures, and so all of the work that we did to make our applications ready for those environments, to make our math libraries ready for those environments, are going to be useful not only on the Exascale machine, but on the broad spectrum of machines that use those accelerators. And like I said, we see, people in the DoD are starting to use E4S in those libraries and experimenting with those. GE is using these kinds of libraries. NOAA is using these kind of libraries. And so yes, exascale computing was expensive, but the benefits that I think we are going to see, for the nation, not only in the, new scientific advancements we'll see, but also in like the earthquake risk assessment maps that we can now produce that we could never do before, or the development of small modular reactors that we can now simulate, the whole fuel cycle, not just the initial state or some snapshot in time. We can look at that evolution over time to develop new, small modular reactor designs, carbon sequestration. There's just so many great applications for this high performance computing and ways in which we can leverage it now that we couldn't do before, that I think the investment is well worth it.
Okay. There's just one question just came in. Maybe we should make that the last question. Do you think the AI technology will be able to redesign or re-implement the existing codes?
So usually when I think about the use of AI technology, I don't think about it as it redesigning or re-implementing existing codes. There are capabilities that can do that to some extent, and they're getting better every day. Where I think AI technology is going to just offer some huge wins is in the use of them as surrogate models. For example, we see a lot of folks moving in that direction where they're taking very expensive simulations. So our wind energy application is doing this right now. They've got a ground truth, high performance simulation of multiple turbines in a complex topography, for like a wind farm development, but it's too expensive to use in engineering design codes. And so they're able to use those high performance computing simulations as training for these AI models that they are now deploying into engineering codes for design of wind farms, either onshore or offshore. And so I think it's those kinds of uses of AI and machine learning where we're just going to see tremendous benefits for the scientific and engineering enterprises and that use computing.
Okay, well, these were a lot of questions you answered, so thank you so much, and thank you for your talk.